A student carried out an experiment to determine the Young modulus of copper. She added a mass m to the free end of a sample of copper in the form of a long thin wire, and the corresponding extension delta x was measured. This was repeated for increasing masses. State the meaning of the term Young modulus. Now, this is the first question we are solving from the topic materials, and in the next 2 or 3 videos, we'll be solving similar questions. And I chose this question first because it covers the basic definitions and details. So make sure you understand this question, because in the next questions, I'll not be repeating these details. I'll just be applying the definitions we learn in this question. So the term Young modulus is the ratio of stress and strain. So you divide stress, which is represented by this symbol sigma, you divide it by strain, which is represented by epsilon. And how do we define sigma and epsilon? Sigma is stress, which is defined as force per unit area, and strain is represented by the symbol epsilon, and it is given by the change in length divided by original length x naught. Remember that strain has no units because it is just the ratio of two lengths, and the units for stress are just force divided by area, so Newton per meter square. If I substitute these in the equation for Young modulus, I will get force divided by area for sigma, divided by, for epsilon, I will get change in length divided by the original length x naught. And if I simplify this division, I will get force times the original length x naught divided by area times the change in length delta x. Also, in some of the questions, you will be given a graph for stress versus strain. So on the y-axis, you'll have stress. On the x-axis, you'll have strain. In this case, the slope, which will be the change in y divided by change in x, the slope of this graph will also give you Young modulus. So all of these are different definitions of Young modulus, but for this question, since it's just 1 point, you can just write that Young modulus is the ratio of stress and strain. The second question is, the student repeated the measurement of the diameter of the wire at different positions and orientations of the wire. She obtained the following results. Determine the cross-sectional area of the sample of the wire. Remember that cross-sectional area of wire is given by pi r squared. And we are given the diameter, and we have different values for diameter. So what we'll do first of all is we'll find the average value for diameter. We'll add all of these numbers and divide them by 4. So you just add them and divide by 4, you will get the result for diameter. And if you calculate this average, you will get 0.234 millimeters. You can find the radius by dividing the diameter by 2. And finally, if you substitute this radius in this equation for area, you will get 0.043 millimeter squared. And finally, if you want to convert these units into meter square, you can write it as 0.043. And for milli, you can write 10 to the negative 3 meters. And since it's squared, you square it and you apply the power. You'll get 0.043 times 10 to the negative 6 meters square. Also, if you move this decimal point here, you can see that I've moved it by 2 places. So I need to add 2 to this power, and I will get 4.3 times 10 to the negative 8 meters squared. The student plotted a graph of mass against the extension delta x. She measured the gradient and obtained a value of 195 kilogram per meter. Determine the Young modulus of copper. The length of the sample of copper used is 3.50 meters. Remember, this length is actually x naught in our equation, which is the original length. And the slope of mass versus extension is given here. So let's see, what do we have here? We know that in the equation for Young modulus, we have force times original length x naught divided by area, and then we have change in length delta x. The slope which the student has measured is for mass against change in length, which means that she plotted mass versus change in length. Now, if you find the slope, you can see that it will be m divided by delta x. But here we need force divided by delta x. So what we can do is we can simply multiply this mass with gravity and make this thing weight, right? And weight will be the force which we can use in this equation. So what we need to do is we can use this mass divided by extension, which is 195. We can multiply 195 with acceleration due to gravity, and this now will give us the weight, which we can then substitute here for F divided by delta X, right? I'll write again here, F divided by delta X can be written as weight divided by delta X, And weight divided by delta x can be written as mass times acceleration due to gravity divided by delta x. This mass divided by change in length is given already. It's 195. You just multiply it with g, which is 9.8, and the rest is given. Then x naught is given, and we just calculated area in the last question. So we can make these substitutions. For f divided by delta x, we'll write slope, which is 195, times acceleration due to gravity. So 195 times 9.8, this is f divided by delta x. We need to multiply this with the original length, which is 3.50 meters, and then you need to divide it by area, which is 4.3 times 10 to the negative 8 square meters. And we can use this area in meter square because the units are consistent. So make sure that if you haven't converted from millimeter square to meter square, you do it first, because here in the numerator we have meters. So in the denominator, the unit should also be meter square, not millimeters. The last part of this question is that the experiment was repeated by another student using a 2-meter length of copper wire. Suggest how the values obtained for the gradient and hence Young modulus will differ between the students. So you see it has 2 points and there are 2 questions. You have to explain how the gradient will change and how the Young modulus will change. Remember that the gradient was for the graph between mass and extension delta x. So what you need to understand here in this question is that if you are using a shorter piece of wire, the extension is always proportional to the original length, x naught. So if you are using a shorter wire, the extension that will be produced will also be smaller. So you can see that for a 2-meter length of copper wire, the extension delta x will also decrease. So it means that the slope will decrease. And what about Young modulus? Remember the equation for Young modulus was force times the original length divided by area multiplied by the extension. So in this equation for Young modulus, you can see that you have the ratio of original length and change in length, which are both proportional to each other. So if the original length decreases, the extension will also decrease, and they will cancel the effect of each other because they are in division. So that's why the Young modulus will remain constant.